Hello folks, my name is Mark Wilson and I'm the founder of AccuModel, where we inspire confidence in hydraulic modeling. Today's video, I'm probably going to break it up into two separate videos because the last one was 15 minutes. That was kind of long, sorry about that. So what we're going to do today is apply what we learned in the first video of EPANET hydraulics, where we showed how the Bernoulli energy equation can be written from one point in the system to another point in the system, and then we can describe the head loss or the energy loss between those 2 points given some flow in the system with one of at least 3 different head loss equations: Hazen-Williams, Chezy-Manning, or Darcy-Weisbach. We're going to choose Hazen-Williams for this video, but you can look up the other two, and that's also available in EPANET based models. Okay, what I've got on the screen here, and we're going to duplicate this in the EPANET software in just a second. We've got a reservoir. We're calling it node 1. It has a water surface elevation or a head of 100 feet. We've got a junction right here, node 2, elevation 0, and we're defining a boundary condition of 1 CFS. That's how EPANET works. You define a fixed demand as a boundary condition. Thus, we'll have demand here, supply here, and a flow from top to bottom. Down here, we're going to use all the same pipe characteristics for each pipe in this video. Diameter of 12 inches or 1 foot, Hazen-Williams C factor of 100, and a length of 1,000 feet. On the previous video, that for the Hazen-Williams head loss equation to calculate frictional losses, or we can also call it head loss, for length in feet, flow units of cubic feet per second, Hazen-Williams C factor, and diameter in feet, we get these coefficients. And EPANET uses what's called a resistance factor. For pipe characteristics that stay constant, which are these here, we can actually combine these factors, and we only have to calculate those once right at the beginning of the simulation, and then the only variable would be the flow. So that's what we've done here. We've combined all this for these pipe characteristics. We call that a resistance factor R, and that works out to be 0.935 for these pipe characteristics and these units. Let's draw a line across here. Now let's go ahead and calculate this out up here. So we want to find what the head is at this junction down here. This is easy with this simple of a system. We can do it by hand, and we'll show a little bit later a loop system and why it gets more challenging to do it by hand and why we need computers to do it for us. So if we're calculating what the new head is down here, we would say start up here at node 1 equals 100 minus the head loss in the pipe. So the head loss in the pipe is 0.935, and we already know what the flow is. It's 1 CFS. That's what we defined here at the junction. So 1 to the 1.852. And so that's the reason why we're using rounded off variable values, so it makes the math easier. This goes to 1 over here, so we're left with a head loss of 0.935. So 100 minus 0.935 is equal to 99.065. Okay, we could convert that head into a pressure down here to see what the pressure was. If you did want to convert this to a pressure, you would divide head by 2.308 is the conversion factor, and then you would get pressure in PSI. We can see that I've drawn the same network in EPANET. Node 1, Node 2, Pipe A. We'll go ahead and run that, and we'll see that for node 2 we have a total head of 99.07. Now let's make this a little bit more challenging. We'll make a new pipe. This will be pipe B. This will be node number 3, and we're going to define a boundary condition here of another 1 CFS. Now we know just by inspection that, let's draw a flow arrow down here, the demand is coming down this way. In this pipe we know the flow is 1 CFS, 1. Now up here we've got to service both of those connections. So up here we've got 2 CFS. So that changes the head loss through this pipe, but actually since we're using the same dimensions, etc., the head loss from node 2 to 3 is going to be the 0.935. Now we just need to calculate what it is in pipe A and then recompute the heads. Okay, so if we want to know the head at node 2, so equal to 100 minus the head loss in pipe A, which is equal to our 0.935 times 2 CFS raised to the 1.852. Okay, if I bring up my little handy dandy spreadsheet here that I've put the formulas in, we can look at what the head loss is for 2 CFS. We see that that is 3.374 feet. And that the head at node 2 would be 96.63. Okay. And then we can subtract that 0.935 from here, and we get 95.695. Back to EPANET, I've drawn in pipe B. You can see the properties there. And node 3, elevation 0, demand 1 CFS. We'll run that. We'll see that junction 2 now has a total head of 96.63. Node 3 has a total head of 95.69. What if we add one more pipe? This is pipe C. Actually, we're going to put 2 CFS of demand at this junction, and you'll see why in a few minutes. So we'll start up here at the top again, and I'm going to do all these calculations on the spreadsheet. So we've got 2 CFS, 1 and 1. So a total in this pipe would be 4 cubic feet per second. This one would be 3 cubic feet per second. And the flow in this pipe should be going this way, 2 cubic feet per second. So the head at node 2, 100 minus, so we've got 87.82, 12.2 equals 87.8. So then the head at 3 is equal to 7.8 minus, so we've got 3 CFS in pipe B and 87.8. So a head loss of 7.15. .65 feet. And then we've got 2 CFS flowing in this pipe, so H4 equals 80.65 minus, so we get 3.374, 77.28 feet. Okay, so we see it just kind of cascades down in a system that is non-looped. Again, back to EPANET, I've added pipe C and node 4, and we see that I've added the base demand of 2 CFS. We'll go ahead and run that, and we'll see for node 2, the new head is 87.82. For node 3, 80.67. Node 4, 77.30. Okay, so next we will look at what happens in a looped system, and I think we'll push that to the next video. So thanks for watching. Please subscribe and like if this was helpful to you so that other engineers can find these videos easier, and check out our website as well. Thanks for watching, and we'll see you in the second part of this video.